And in chapter 13, we had asked you guys to, or we had done some definitions and shown you how to do some stuff on the calculator and talked about a new notation for describing end behaviors called the limit notation. I think I asked you guys to work on 1 through 8 from the problem set. Does anyone have questions on any of those things before we move forward? Yeah, Joe?
Could you number 5, please?
Uh-huh. All right, so 5 asks us to describe the end behavior for this function using limits. So to do that, I'm going to just take a look at the graph. And I'll just start by typing in my equation. So negative 4x to the 6th minus 7x squared plus 5x minus 6. Cool. Before I go ahead and hit graph on this, what I'm going to point out to you guys real quick is I notice that this is a polynomial, the function that I'm graphing here. Polynomials are always only going to have 2 end behaviors, one as x goes to positive infinity and one as x goes to negative infinity. So like right away, I can start with this already, right? So I'm even able to write in the subscript there for what the x is approaching because I know these are polynomials and all I have is the left arrow and the right arrow to have to worry about. Okay. So since that's the case, rather than mucking around with the window, I'm just going to do a zoom fit and let the calculator pick an appropriate window for me because all I really care about is whether these arrows are pointing up or down. Calculator, what are we doing here? That seems unlikely. Did I fat finger something here? Yeah, okay. So just the calculator zoom fit did a poor job of picking. Anyways, here's my graph. I had to do some guessing as far as the window goes to get that to show up. But the part that I care about is that the arrows are both pointing down at either end. We good with that? So what that's telling me is that the y-coordinate is approaching negative infinity. So that's it. If I'd asked for a table to justify this, that would be a different story, but I don't, so all I need to really do is look at the picture and use the limit notation. Okay. Yeah, no problem. Anybody else here on these? Okay. All right. Before we get started, let's just kind of do a little outerwear check. I know some of us are just getting in. Yeah. If you need to run to your locker, that's fine. Grace, I don't know if that's a Notre Dame sweatshirt or not. Okay. Then you're good, I think, right? Okay. All right. Hi, Ashley. So let's then start section 3, 13.2, had a 3 in it. So we're going to be talking in section 13.2 about zeros of polynomials. Remember from the last chapter that we used the term zero and X-intercept? Yes, of course. We use zeros and X-intercepts interchangeably, right? So don't get thrown on that when we're talking about the zero for a function. We're just talking about the X-intercepts. So what we did last time is we talked about finding these zeros graphically by using our calculator. What we're going to start talking about here today and then the next lesson is talking about doing this algebraically, like with pencil and paper. So let's start with a simpler example. Okay. Everybody's okay with this? Looks familiar, like a problem we would have done last year, right? Right away, I know that because the degree of this polynomial is 3, I'm looking for at most 3 zeros. Could be less, but it has to be at least, can't be more than 3. Everybody's okay with that? So to find the zeros, all I'm going to do is set my polynomial equal to 0. Everybody's good there? And now to solve this, what I'm going to do is rely on the factor tree that we used last year. Does anybody remember the first thing we need to check on the factor tree that we used to factor a polynomial? Okay. Well, the very first step would be looking for a greatest common factor. So if I look at x cubed minus 6x squared minus 8x, do you guys see a greatest common factor there? You should, because there is one.
How about 48?
Well, that would be the least common multiple.
Oh,
So that's different from the greatest common factor. So the greatest common factor would be something that divides each term evenly. Not 2, because 2 doesn't divide a 1. But there is a greatest common factor here. Eric? It is x. Yeah, we don't have to just look at the coefficients. We also care about the variable parts. So I'd want to start by factoring the x out. So when I do that, x cubed becomes x squared becomes x, and 8x just becomes 8. Does everybody feel okay there? Once we've taken a greatest common factor out, we're going to ignore it until the rest of our factoring is done. It's just going to stay there out front, but we don't need to worry about it when we consider factoring the other parts of it. So if I look at the remaining piece, the x squared minus 6x minus 8, can I factor that anymore? Well, if I go down my factoring tree, the next thing I look at is the number of terms. In this case, how many terms do I have in that piece in yellow? 3. So, okay. If I can factor this by hand, it would have to be in the quadratic form. Is that polynomial in the quadratic form? Yeah, and in fact, it's actually a quadratic itself, right? X squared minus 6x minus 8. Okay, so it is in the quadratic form. For things in the quadratic form, the next thing I want to check is the leading coefficient. In this case, the leading coefficient on that piece in yellow is 1, which means that I can do this with the factoring shortcut. So to factor a quadratic, I need to find the two numbers that multiply to give us, in this case, -8, and add to give us, in this case, -6. And there was an error in my example. I'm going to want to make that plus 8x because it was not factorable before. So I want to make sure that I fix that real quick. My apologies to you guys. Are there two such numbers? Multiply to give us +8 and add to give us -6. There are. They would be -4 and -2. So far, so good. Now that we've got this into a factored form, I feel pretty good because either I have a monomial or I have a monic term. That means that the factor has degree 1. So that's how I know I'm done. So what I can do now is I'm going to apply the zero product property, which says that if I have two or more things that are multiplied together and they equal 0, at least one of those things is equal to 0. So because this is a multiplication problem that is equal to 0, I can just take each piece of my multiplication and set it equal to 0. I cannot do that if my multiplication problem is not equal to 0. This is special. You need it to equal 0. Well, to solve x equals 0, there's nothing to do there. X minus 4 equals 0. We'll just add 4 to both sides. X minus 2 equal to 0. We'll just add 2 to both sides. So we'd say that our solution here, or we'd say our zeros are at 0, 2, and 4. They don't really need to be written in ascending order like that, but I would usually choose to write them in that way just because, I don't know, I'm a math teacher and it feels like the most natural way to write them. But the order there is not important that you write those zeros. Feel okay? Let's do another example. Morning, Domenico. What should we do first on this one? Excellent. Do you guys see a greatest common factor? X, yep. So we'll set this equal to 0 and then factor off our greatest common factor of x. Okay. The polynomial that remains after that is quadratic. Its leading coefficient is 1, so we can use our shortcut to factor this. So we just need something that multiplies to give us +9 and adds to give us +6. What are those two numbers? 3 and 3. So I could write it this way, or you could write it as x plus 3 quantity squared. Either way is fine. So when I apply the zero product property, I have x equals 0, nothing to do there. I'll subtract 3 from both sides to get x equals negative 3. And I'll subtract 3 from both sides to get x equals negative 3 again. Notice we're getting the same answer more than once. When this occurs, we call this a multiplicity. And because it happens that we get the same answer twice, we'd say the multiplicity there is 2. So for the 0, x equals negative 3, we'd say its multiplicity is 2 because the solution occurs 2 times. If that solution occurred 3 times, we'd say its multiplicity is 3. Now when we count our zeros, we only count the 0 one time. So we'd say that this has 2 zeros. So notice this is a situation where the degree was 3, yet we end up with only 2 zeros. Remember our theorem from last time says we have at most n zeros, where n is the degree. So in the case where you have less than n zeros, it would be a case where you have some multiplicity going on. Or one other situation, let's look at that. So let's say we have f of x equals x cubed plus x squared plus x. Again, start by setting this equal to 0 and then looking for a greatest common factor. Do you guys see one? X, right? Can factor that off. The piece that's remaining, is that quadratic or in the quadratic form? Yes. Its leading coefficient is 1, so we can use the shortcut factoring. So looking for something that multiplies to give us positive 1 and adds to give us positive 1. Oh no. Does that work? No. So what do we do if we can't factor that? Well, we just still can apply the zero product property, right? So x equals 0 is certainly a solution. But how do we solve something quadratic that we can't factor? We can use the quadratic formula. You guys remember that? Now that I put it up here, at least like, okay, that looks familiar. I remember the name. The nice part here is that my A, B, and C are all 1. So I have x equals negative 1 plus or minus 1 squared minus 4 times 1 times 1 all over 2 times 1. So 1 minus 4 is negative 3. And uh-oh. Why does Mr. Kulik saying uh-oh here? Yeah, I have a negative under the square root. What does that mean? Yeah, it means that that's an imaginary number, so that we generate an I and replace the square root, or replace the negative under the square root with an I outside the square root. This is a non-real number because of the I, and hence it doesn't contribute to the zeros. So here our zeros is just 0. You okay with that? Okay. I want to circle back to this multiplicity idea. So we have a polynomial, or let's say, if the graph of a polynomial function has a 0, let's say X-intercept, that passes straight through the x-axis, then that 0 has multiplicity 1. So passing straight through, we mean something like this, right? The dot's my x-intercept. The graph is just passing straight through. So if that x-intercept bounces on the x-axis, then that 0 has an even multiplicity of at least 2. So here you see our x-intercept there. We call that a bounce, where it hits the x-axis and then just goes back the same direction it was coming from. Kind of looks like if a ball was bouncing on the ground or whatever.
Did we do this last year?
We did. We did. And the last one is if we have an x-intercept that bends as it passes through the x-axis. Then that 0 has odd multiplicity. At least 3. And what does a bend look like? It looks something like this. Where it looks like I have, highlight. One half of the bend looks like half of a bounce that should be going down, but the other half looks like a bounce that should be going up. Right? It's like half of opposing bounces. You guys kind of see that? So this is nice, as it gives us a good way to predict when we get when we should expect a multiplicity, because we can just look at the graph on our calculator, right? Okay. Let's do a story problem example, and then we'll continue on and look at some furthering finding these zeros. So let's say that this example is like a story problem example. Let's say we want to design an open top box. And we're going to build this from a single sheet of cardboard. And we're going to do this by cutting a square out of each corner of the cardboard. Our box needs to have a volume of 500 cubic centimeters. And the piece of cardboard is 26, well, let's make this the same unit, inches by 20 inches. And we want to ask what size squares do we need to cut from the corners? So the scenario is basically you want to build, something like this, like a box that opens up, right? Our starting material is just like a rectangle of cardboard. And we're told that one side is 20 inches and the other side has to be 26 inches. And the volume of this box when we're done needs to be 500 cubic inches. Everybody's okay so far with kind of what I've sketched out? Okay, Important geometry related question. Anybody remember the volume? How to find the volume of a box? It's an easy formula. Just take a guess.
Is it base times height?
So area of the base times the height. So in our case, it'd just be length times width times height.
Yeah.
So that's good. So, and we know that the volume in our case needs to be 500. Okay. But we don't know how big these squares we have to cut out of the corners are, right? We're just going to be cutting out some square from each corner. And they're going to be the same size squares, even though Mr. Kulik can't draw two squares that they're about the same sizes in his picture because drawing on the tablet is hard. Everybody's okay with that? So here, this side would be like our length. This would be like our width. And when we fold things up, that piece would be like our height. Actually, let me use 3 different colors here. I'll put it over here or something. Is everybody okay with that? Dimensions wise or whatever? Should probably makes it, ooh boy, ew boysy. Probably more natural to think of this as the height. Because when you fold that piece up, that's what's sticking up, right? Okay. So right now, if I just say 500 equals length times width times height, that's not very helpful because I have 3 variables in the same equation, right? I have L, W, and H. Can't really solve 3 variables in one equation, so that's not super helpful. I need to rewrite this in terms of a single variable. The single variable we're going to be looking for is x. So clearly height is just x, right? We can see from the picture how I've drawn that. Everybody's good with that? What does the length have to be? Well, I know the whole side is 20, right? Everybody's agree with that? But we've cut out this section and this section. So how long was each one of those sections?
Did you say 5, 25%?
How about their x, right? Because they're the side length of the square. That's what we don't know. So really, this would be 20 minus 2x would be that length. You guys buy that? Since we've cut off 2 x length squares, we're chopping x off one end and x off the other. Does that feel okay? All right, with that, what's the width going to be? 26 minus 2x. Excellent. And now, when I put this together, length, we have 500, equals length times width times height. Everybody feels okay? What do I have to do next? If I want to solve this thing for x, right? Because that's going to give me the length of the side of the square that I have to cut out. That's what the question's asking for. If I want to solve this for x, what should I do next? Yeah, let's FOIL that bad boy out. I've already done the foiling by hand. Can I just write down the foiled out result? Okay. So I get 520x minus 92x squared plus 4x to the third. Okay, good. Now what?
Now we have to find greatest common factor. What's it called?
Greatest common factor is the term you're searching for, but we need to do something before that. What does this equation have to equal before I can start factoring things? Becker?
0.
0. Needs to equal 0. Right now, what does it equal? 500. What's going to be the easiest way to make this equal 0? Subtract the 500 from both sides. And I'm just going to rearrange the terms here so that they're in descending order, which is kind of the more natural way of doing that. So here's what we have then, right? What do you want to do next? Now, as Joe suggested, we should search for a greatest common factor. Do you see one? Two doesn't divide 9. Oh, thank you. My apologies if you're listening at home to hearing that giant sneeze in the middle of your video. You're awake now, though.
I don't think there is.
There isn't one. Very good. So we're kind of at a factoring impasse, right? What can we still do, though?
We can't do the quadratic formula. It's not quadratic.
We can't do the quadratic formula because this is not a quadratic, it's a cubic.
Is there a cubic one?
There is, but you don't want to see it. What if we go back and do the same thing we did in the first section, where we just look for the x-intercepts using our calculator? Right? That's still a viable option. That never went off the table. That's what I would do. So I'm going to do 4x cubed minus 9x squared plus 520x minus 500. Then I'm going to set my window. And here I need to use a little bit of common sense, right? So x is representing the side length for one of these squares. What do we know about side lengths of geometric figures? What kind of numbers can't they be? Negative. So my x-min should certainly be 0, right? We can't have a negative side length for a square. Now let's think about the specific situation we have here in our picture. What is the biggest value that x can be? What's the biggest side length we could have for that square? Bigger than that. Let me tell you. It's 10. Why is it 10?
Wait, how can it be 10?
Well, because if this is 10 and this is 10, that's as big as this cut you could have and still be able to cut the 20 side, right?
Oh,
So it basically takes up that entire side length if both of them are 10.
okay, that makes sense.
Couldn't be any bigger than 10, certainly, because now you're cutting like impossible, right? You're making that side length L negative, which we know it can't happen. Does everybody feel okay there? All right. So go 0 to 10. Now the y here is really representing volume, right? Because that's what this equation was equal to. What's the smallest possible volume we could have? 0, right?
Oh, yes.
Yeah, just can't have negative volume, but we'll make 0 there. And what's the target volume we're looking for? 500. So I'm willing to go maybe like a little bit above 500 or whatever, but, you know, not a big deal. Now, really what we're looking for, though, is the X-intercepts, right? Would be helpful maybe to see where the thing is crossing. So maybe rather than doing X-min at 0, I'll do like negative 250 or something, just so it's easy to see where it's crossing the X-axis. Okay, so it shot off the screen, but that doesn't matter because the only feasible value for X that I care about is right here. So let's find that with the good old second trace. Which command did I use to find X-intercepts? The 0 command, very good. Remember, zeros and X-intercepts, we use those terms interchangeably. Now it asks for a left bound. Currently it's saying my cursor is at 3.9 and 1,600, so it's like off the screen. So I'm just going to keep pressing the left button until I can start seeing my cursor. There it is. Need to move it on the left side of that X-intercept. So down there looks good. Somewhere on the right side, press enter again. Guess, it doesn't matter. So 0.97 is what I get there. Okay. And I think as I'm looking through my notes here, that I think this is actually supposed to be 420. And that means our answer over here is going to probably be a little bit different. Oh, Mr. Kulak. Mistakes happen. Oh my gosh, guys. Okay, so I made like 100 typos on this. This was all supposed to be minus 92. Oh, Mr. Kulak. This is what I get for just not foiling it out by hand and trusting my own previous. Do you ever have one of those days where just like you can't seem to do anything right? That's happening to me right now. Oh, there we go. That's more what I expected. I did expect to see 2 answers here. All right, try this one more time. Left bound, right bound, guess. So 1.96. And then the other one. Do it again. Left bound, right bound, guess 3.67. Sheesh! What a mess. I made it worse than it had to be, because I made a bunch of dumb mistakes. Because apparently I can't copy down something from a sheet of paper effectively at 8:25 in the morning. It happens. It happens. It happens. Okay. We're going to start section 3 here, but we won't be able to finish that. But that's okay. I just want to walk up to one idea, and then we'll call that good for today. Okay. Go put on our time machine hats. We're going back to elementary school and talking about long division. Yeah! So let's say we have 76 divided by 13. How did we set that up?
13 on the left side.
Mm-hmm.
Little baby.
Mm-hmm.
Yep. 76 on each side.
Okay. And then what did we do?
Try to see how many times 13 goes into 76 without being greater than 76.
Okay. So how many times is that? 5 times 13 is 65. 6 times 13 is 78. So 5. So we do something like this, right? So what we're saying here is that 76 divided by 13 is 5 plus 11/13. Everybody's okay with that? So what we have is we have the dividend divided by the divisor is equal to the quotient plus the remainder over the divisor. We're going to take that same idea, but now apply it to polynomial functions. So we'd say that f of x divided by d of x is equal to q of x plus some r of x over d of x. But it's really the same idea. It's the same idea as what we did in elementary school, but instead of using numbers, we're using polynomials. And remember that division and a fraction are the same thing, so oftentimes we write it like f of x over d of x. Division and fraction is still the same thing. All right, so let's do an example. Let's say we have 2x cubed minus 4x squared plus 5x plus 1 divided by x squared minus 3. So how are we going to set this up? So we're going to start the same way. What's going to go on the outside? X squared minus 3. Okay, what's going to go underneath? The numerator. Now there's one thing that I would do here that I think makes life a little bit easier. Notice the numerator goes x cubes, then x squared, then x to the first, then a constant. And I don't skip any terms there. But if I look at the divisor, I go from x squared straight to constants. And we've skipped which term there? The x term. What I'm going to do here is I'm going to write in a 0x there, because it's just going to help when I do the multiplications and subtractions and things. It's going to help make sure everything lines up. Okay with that, Joe?
What would happen if you put a 1x instead of a 0x?
You'd definitely get the absolute wrong answer.
Okay.
Yeah, has to be 0.
It has to be 0.
Yep. Okay. So what we're going to do is we're going to ask ourselves, what times x squared gives me 2x cubed? What? You mean 2x? 2x. Now, whenever I ask this question, I am only caring about the leading terms. I don't care about what's happening after that. All I care about is the leading term. So there's the 2x. And now I'm going to multiply this to all of the divisor. And I'm going to write my answer underneath. Is everybody okay so far? Okay. And when I looked at the long division before, I did 5 times 13. I wrote the 65 there. And then what did I do with the 65 after I wrote it there? Subtracted. What are we going to do here? Subtract. But the place where I see students most frequently make their mistake is they forget to distribute the negative when they're doing this subtraction here. So really when I do this, I'm going to distribute the negative before I start doing anything else. And I'm always going to think about this really as an addition problem. So I'm going to distribute the negative, make things negative where they need to be, but I'm always going to think about it as an addition problem, so I can just add straight down, and I think it's a little bit simpler. So here, 2x cubed plus a negative 2x cubed, 0. That's gone. Negative 4x squared plus negative 0x squared is still, well, that's still just negative 4x squared. And then I have 5x squared plus 6x squared gives me 11x. I said squareds. I didn't mean to say squareds. And then the 1 plus 1 I'm just going to bring down with me. Is everybody still doing okay? So let's put up. We're going to need to do it again. So we're going to ask ourselves, what times x squared gives me negative 4x squared? Negative 4. I'm going to multiply that to each piece of the divisor and write the result below. And then we'll subtract down. But really, we don't like to think about this as subtraction. We're going to distribute that negative through. So that becomes plus, plus a negative, plus a negative. So far, so good. We add down, and we have negative 4x squared plus positive 4x squared, that gives me 0, so those just cancel out. I have 11x plus a negative 0x, well, that's just 11x. And I have 1 plus a negative 12, that's negative 11. And at this point, I know I'm done, because if I compare the degree of what's left to the degree of the divisor's degree is bigger, right? Everybody sees that? Nothing, I can't multiply any polynomial times x squared to get x. So this piece here just becomes my remainder. So the way we'd write our final answer then is 2x minus 4 plus 11x minus 11 over x squared minus 3. Yes, sir.
So does the remainder just act as like a plus sign?
So, yeah, when we talked about our initial format here, it was always plus the remainder. Now, the remainder might have a negative sign in it or whatever. But, like, you know, like I could, if I did this, I could write it that way, and it's the same thing. But, like, I don't know why I would ever do that.
So just follow the formula after you solve it.
Yeah.
To rewrite it.
Yeah. Yeah. That's all you need to do. I'm not going to be super picky about whether you like pushed a negative sign through or pulled a negative out or whatever. Like, you know, like just write it as plus the remainder over the divisor, whatever that remainder is. And again, this was something we did last year, right? Should look familiar. Not totally foreign. I think this is probably a good place to stop with the long division piece. We'll review this again next class, the long division piece, and then start tacking on about how this relates to solving, since it's really kind of what we're after here. So at this point, you guys should now be able to do up to 19. But this will be on for not this Sunday, but the following Sunday, right? So the only thing due on Sunday is going to be the 1 through 8. And then the following Sunday, we'll worry about this piece and then whatever else we're able to do next week. Reminder, next week, Thursday and Friday are our virtual days. I assume they're going to be asynchronous. I haven't been given that information yet, but that would be my suspicion. So probably what I would prefer to do would be to kind of do maybe more lecture stuff on Monday, Tuesday, Wednesday, and then leave like Thursday and Friday as like, hey, just kind of, we did more than we would usually do in these 2 class periods, so that we can just kind of pause and work on catching up on some homework kind of in those asynchronous days, so that we can just make sure we're kind of good to go. We are entering section 3, so what should you expect next week? Homework quiz. So just kind of keep that in mind. We have just 1 class day next week, right? So it probably gives you a good idea of when to expect to see that if we're expecting it next week. So, okie dokie. All right, let's call her good.